Hi everyone. I'm realizing I have this last example for integration by parts, and it's a good one just as is, but we haven't done one yet where it's a definite integral, and that's important to talk about. It doesn't end up being very tricky, but there's just one or I think really just one thing that you have to be aware of. Okay, so looking at this, I definitely have a product, k squared e to the k over 2, and this is supposed to be like a k over 2 in the exponent. And I'm supposed to integrate from 0 to 1, so I need the antiderivative. That's not trivial. By parts is a good candidate here because two things. One, it is a product, but so are substitution problems from the chain rule. The other thing that's really big is if I pick out, say, this as an inner function, I don't see its derivative floating around. So it's like products of two fairly basic functions as opposed to a composition multiplied by something a little simpler. So that's what we're looking at here. There is a little composition with that e to the k over 2, but it's certainly nothing that would wipe out k squared for me. Okay, so let's see, if we think about y8, it says algebraic is going to trump exponential, so I'm going to let my u equal k squared. This one's always my favorite anyways, because it just nicely wipes out that term. So the derivative of that is a 2k. We move the dk up. This means that for dv, I get e to the k over 2 dk, which means my v is going to involve an e to the k over 2, but I have to be careful about the chain rule. The derivative of e to the k over 2 is e to the k over 2 times 1/2, which means if I don't want that 1/2 showing up when I'm all done, I need an extra 2. So there is my first round of parts, and it gives me u times v, so here I'm going to put the 2k squared e to the k over 2 minus the integral of v du. I've got two 2's, so I'm going to move 4 out in front, and then it's a k e to the k over 2 dk. Okay, so there's the by parts. We can't forget about the limits of integration. They're really easy here. They just carry through. I don't think that's too shocking. What you want to remember is that we have not changed variables. We've just worked backwards through parts of the product rules, so it's still all k's. K still stops at 0, or starts at 0 and stops at 1. The thing to be careful of is you can't forget that this guy also needs to be evaluated. So writing that somehow so that you remember that you're not just going to evaluate the thing you get out of the second integral is like the one tricky detail. The other thing I'm seeing here is that I think I've made an improvement. I've got a k instead of a k squared, but this is still a product. So I'm actually going to do a second by parts. Again, algebraic trumps exponential. So the k is going to be my u. And then the e to the k over 2 dk is going to be my dv, which is the same as last time, so we already know that there's a 2e to the k over 2, oh, no more dk for my v. Okay, so now I have k squared e to the k over 2, and you can keep the 0, 1 stuck just on this, but really the truth is that everything that we end up with should get evaluated from 0 to 1, so I'm just going to go ahead and incorporate this all in at the end. Ooh, am I? No, I'm going to go ahead and keep this for now because we're going to have one more integral. So we have a 4 times, where is it? This. So k times 2, so 2k e to the k over 2, which is going to have to get evaluated from 0 to 1, minus the integral of v du. Okay, oh, and I'm going to go ahead and move that 2 out in front because I've been making a big deal about that. This is 0 to 1. So I've made a pretty big mess, but it's all doable. I'm going to go ahead and do some distributing, so this minus 4 has to multiply in. And 2k squared. I guess we don't really need the bracket. We can just use the vertical bar like I did on the second one. From 0 to 1. And then we're going to get a minus 8k e to the k over 2 from 0 to 1. And then it's going to be a plus 8 times the integral of e to the k over 2 dk. And we're close. Okay, so we get 2k squared e to the k over 2 minus 8k e to the k over 2. Since I'm going to be done integrating here, I'm saving up that evaluate stuff for the very end. Plus, the antiderivative of e to the k over 2 is 2e to the k over 2. We've done that one a couple times before. And now, oops, that needs to get multiplied by the 8. Don't lose that, so we're going to make that a 16. And now I'm just going to say all of that gets evaluated from 0 to 1. So just make sure you realize that as you spit stuff out in front of the integral, that doesn't mean it's not part of the whole evaluate thing. When I plug in a 1, I get 2 times 1 times e to the 1/2 minus 8e to the 1/2 plus 16 e to the 1/2. When I plug in 0, I get 0 and 0 and 16 times e to the 0, which is just 16. So when I'm all said and done, I have negative 6. It looks like I have 10 square root e's. Fine if you leave it e to the 1/2 minus 16. And that's my answer. Okay, so a little bit of a messy one, but certainly doable. And just remember that the limits of integration have to apply to everything you end up with when you're done with all of your integration by parts. Thanks for watching.